Well, thank you so much for attending. We're from Konrad Technologies, Becky, Linton. Let's present, and me, Luis. What we're going to be presenting is developing a simple API for a complex test system. We're going to try to explain a little bit what we've done with a very complex system and how we achieve to simplify it. So first of all, a little bit of Konrad. Our headquarters are in Germany, but we have several offices in the US, in China, and across Europe. And also we have an office in India. So first, Becky.
That's me. Some of you already know me. I'm a certified LabVIEW architect, LabVIEW champion, been programming in LabVIEW for years and years. I'm going to let Luis run most of the program and try not to interrupt him. We did work together on this project. The way Konrad runs test projects are we have a technical lead who makes a lot of the architectural decisions, and we put together a team of engineers that do the work in the end. So when Luis is talking about an API and things, I helped him with the slides a little bit, but this is mostly him all talking about it. And so I wanted to let him run with it. But before we skip to Luis and his background, I have two questions for the audience. Who in here has used the NI PXI 148X card, the 86, 87, 88, 89? Two of you. All right. Who in here has used the Flex Rio cards, any of them that have a getting started example? Did you guys love that API they gave you? Wasn't that an amazing driver? No? It was okay. So this is kind of a little bit of a story of our history, how we started with that and got to a reusable API. But one more question. I know the session before this was Intro to DQMH. Who in here knows nothing about DQMH, has never touched DQMH? Okay. So we did use DQMH for our API, and we are going to say why, but we may have to go into a little more detail on that, on DQMH or some of the decisions there. So there's some reasons we did that. Fab will probably be super happy that we used DQMH for it. But all right, Luis, go ahead.
Okay. Well, this is me. I've been working in Konrad since 4 years ago. And let's start with the agenda. First, we're going to be talking about what is an API, a little bit introduction, try to remember about APIs and where we can find them. We're going to give introduction to SerDes cameras, which SerDes is serializer, deserializer cameras. And we're going to continue using this acronym. A little bit of application examples and where you can find them. I mean, we did an application, but there are a ton of applications that we can do. And a little bit on the inside of how these cameras communicate. We're going to review the Flex Rio cards, go through where we started the API, which was a getting started example that we started from LabVIEW. And then we're going to run through that solution and why we decided to choose this one. And at the end, we're going to go through the minimum hardware system needs in case you want to start with the cameras. So what is an API? You probably heard the term, but do you know what API stands for? Does anyone in the room?
Joe, the sales guy got it. Good job, Joe.
Thank you, Joe.
We're the reason that the acronyms exist, right?
Yeah.
Yeah, a lot of people don't know what it stands for.
They don't. A lot of
You'd be
people.
surprised.
Yeah, you'd be surprised.
What about ADE?
I don't know. Today's API.
Oh, I usually go IDE, integrated.
Yeah.
Anyway.
So yes, application programming interface. But let's review what each of these words stands for. But which application? Like basically any software or system with a specific function. In this case, one that you develop or one you want to use. And interface, which is the second word, would be like, what are you connecting? We could do user system or system with systems, but also the third one that I put, it's a user with another user. For this is just us. And we usually use our language and culture as an API because it's how we communicate to each other. And I put culture here because sometimes you could just talk to each other, but there's a lot more involved when you communicate with somebody else. And lately, the interface, which is explaining what is getting together. In this case, it's going to be either controlling an instrument, a port of the instrument, communicating through it, a link to a database. I mean, the rules of engagement in which we want to use the API. Where can we find them? I like to put this example because, I mean, I bet a lot of people know this dream machine that we used to have next to our beds while sleeping. It's an old clock. And I like it because it's very basic. The only way you can change the hour or set the frequency to work is just by using buttons and dials. There was no touch screens or anything fancy. And this was basically the API that we had for this. We can find them everywhere. Like Windows, LabVIEW has APIs inside it. I mean, basically the APIs are our tools that we use to communicate. Toolkits can also be a type of API. We use them, we install them, but it's also that we use them to communicate with something or do something with our software. And then frameworks also, they have APIs. And when we try to do something with the framework, we get help with the APIs that they have. I list here a little bit of the applications where we use APIs with your drivers, toolkits, probably using APIs on palettes. Once you install it, you can start using it right away, and the palette's just a quick way to start using the API. So, from the audience, which is the most common hardware API that you used in LabVIEW, in the LabVIEW environment?
Visa.
Very close. it's a good one. Oh. Well, actually, the answer is Documex. It's very, very common. I mean, almost all LabVIEW developers have stumbled through this one. I mean, very easy. And it's a very good example of API because you can use it to do all the functions on Documex. Like you can create a task. You can set the timing settings. You can just decide how much you're going to be reading from the DAC channel. So basically, the Documex API, it's a very good example of that.
And I'm going to pause because I think Luis and I took the Documex API because this is what we wanted from the Flex Rio cards. Like, this is what we're used to from NI. We're used to Visa. We're used to Documex. We're used to something easy to use. I can do individual channels. I can do multiple channels. But for those of you with experience with the Flex Rio card, is that how those work? No, not at all. So, and I didn't give us exactly, I understand where they're going with for it, but this was kind of the inspiration is we started with the getting started example, but we're like, but we want Documex. So how do we get there? And so Lisa's still going to go through some of the background on the cards and stuff, but I wanted to pause and kind of say, this is the inspiration we had.
Yes. Reviewing a little bit on toolkits and APIs that we can find. I mean, just to list some of the ones that we use the most, JSON text. We probably used it for parsing JSON strings from Dr. James Powell. I like this one a lot because it's very easy to use. NGI Panel Manager is also a very good API that you use, and it solves a lot of issues trying to arrange your panels and using them and loading them in LabVIEW BIs. And to list one of the frameworks, DQMH. The API from DQMH helps you a lot to interface with all the needs that you want to do with the framework. I mean, you can use, like, for example, in QE, the QE events by just using the API that's already installed when you work with the DQMH framework. So let's look up for more APIs. And while trying to solve the problem for a project that we had and these Flex Rio cards, we started looking with the NI example finder. It's a very good place to find APIs. I mean, you can find Documex, examples of it, but also you can find more advanced APIs. And we, in fact, working for the 1487 and 1488 cards, we found that the examples of these cards were actually generating code, which is not common to find in the examples. That is usually a project template. And we're going to run through this one. But the important thing here is that we're getting code that it's lately used as an API from an example that we look up on the example finder. So how do we create an API? Things to take in mind when creating the API would be the developer or the person who is going to be using it, the skills of your team, because if you do it very complex and your team is not knowledgeable about it, then probably it's going to be very hard for them to use it or to extend. And that's very important. And if they know design patterns, frameworks, something else, that's very good too. Things that you would need for your API. And this is one of the things that I started using is like, the API is going to solve your problem, but first think about the things that are reachable for you. What are you getting? Like in this case, we just have a camera that we need to connect. So we have an FPGA. So first thing would be your bit file reference or bit file path. And what else you have? Like, where is your PXI card? So those were our first inputs. And later we started with defining which camera, if we need a specific script to program the camera, or if we needed to know the size of the images we were going to be getting. I mean, those are going to be your inputs. And the resources that you need for that, like for example, Flex Rio, we need a special DLLs to work with it. In this case, we have several libraries. So even though we create one library, probably we're supporting with other ones. Like if we use the toolkits, that could be one of our dependencies. And if we're going to be talking to other libraries to be available also for you. When creating the API that we created, we thought this was a very good way of designing the software of our API. And that is S'mores. And I give credit to Norman Kirchner here of a previous talk that he had.
Norm's not here, but I'm like the person who preaches s'mores left and right at Konrad. Everyone has had to listen to me talk about it. So Luis put this in here for me, I'd say, because I think he likes it too. But if you guys have not seen the presentation on s'mores, has anyone in here not seen this ever? Raise your hand. You've all seen it? You've never seen it? Okay, Google it online. Everyone likes s'mores, they're tasty. So when I'm doing code reviews, especially for my younger engineers or interns, I'm like, I want your code to be tasty. If not, I'm throwing it out, I'm throwing it back at you. And so there's this idea of keeping your code scalar, modular, reusable. He's got optimized in there. I kind of just use modular and use the O in there. But reusable, extensible, and then simple. And having that S second makes sense. And there's a whole acronym, and there's ways to describe each of these and true LabVIEW examples of when it makes sense to and when not. So there's the example of, I need to do something super simple. Don't do full s'mores. And I'm going to give a little bit of history of this because I think it's important as Luis continues talking. Almost 10 years ago, I think it was 2015 or 2014, this particular customer, we've built over 150 test systems for. About back then, I did a s'mores presentation to them. I'm not joking. Same presentation to the customer, telling them, every time you do this, you're wasting your resources. You need to spend some time up front. Let Konrad develop a framework for you. So we developed this framework using TestStand, using LabVIEW that allowed us to break out hardware modules. And we used DQMH. It was one of the early versions of DQMH, but we did. And for good or bad, I got to go away for the next 8-10 years, on Konrad other projects. And then I got put back on it last summer and I'm like, ugh. There's certain things I don't like that I did. So that's just another warning to yourselves to be nice to your future self, because even code you may think you're done with, it's going to come back to haunt you. So some of our PMs are a little bit not happy with me. Luis can talk about it because I'm like, there's some things you guys did to my framework along the way that's not so good. You've got some intermixed dependencies. So we did spend an extra couple weeks breaking it apart. Everything's PPLs. I think we have 42 separate libraries at this point. And this was a new extension, a new type of hardware we added to theirs. They were using other hardware for testing cameras, and now they're using the NI hardware.
That's really cool. Besides this API documentation, like Becky mentioned, you don't know when you're going to be coming back to work on the project or extend what you already have in your project. So I list here 2 things, very important ones, which is documentation for the people who are going to be developing the library or the API. Because if you bring more engineers on board, either you need to be teaching them like how code works, or you need to be looking for the people that created a specific piece of code and then make him explain the rest of the team. So if you have this documentation which explains this, you don't need to worry about this. And also, because we're used to creating API for example, if we just do the API, somebody's going to be using it, but we sometimes forget about people who might be extending the functionality of our API. It's very common that just build the API, how to use it, and that's it. But when you need to extend it, then you need to review what's happening in the inside. So that's a thing to take into account. I always say that the API needs to be like a book. And the analogy is if you write a book that nobody's going to read or doesn't understand how to read it, it's going to be very hard for people to read your book. Even though the book might be awesome, nobody's going to read it because it's very hard to read it. Nobody would understand it. So the same for the API. Try to create something like if you want somebody to use it and read it. And people are going to be using that, and it's going to be really reusable and useful for your team or the community. And going back to the example of the radio, what if we convert that into LabVIEW? We would have small VIs taking the function of every button and dial. What if we group them? We could have a library. And then that library could be turned into your API. And to define a little bit more on this, they have the same purpose. They have a specific functionality they do, each of them. And these API is going to have its own identity. So what I mean this is not only, it's like when you grab a new library or an API that is very easy to use, you like to use it and reuse it because it's very easy. But when you move into another one and you know that one is complex, it's like you know that it's going to be behaving different. Or like Visa, for example. You always know that the top left connector is always going to be Visa. And when you grab another Visa VI, you kind of expect to be there for you. So it's the same way. Every library has its own identity. And we can convert that library into a PPL. And this is just going a little bit further on our APIs.
Who uses PPLs?
Huh?
Real quick, ask who uses PPLs.
Yeah, that's a good one. Do you use?
No PPLs? Okay.
Does everybody know what PPLs are?
Project libraries.
Yes. Yeah, I mean,
Packed ones, yeah. It's a deployed version of a library.
yeah, we don't always convert them to PPLs, but yeah, exactly. Once you start deploying them, you want to make them PPLs. So they're very good for versioning, very easy to transport. So you can just copy them and know which one is running. And if you do changes, it's very easy to track them. So think about a library converting into a PPL.
Easier for installation later,
Yes,
rather than discrete VIs. Makes sense.
definitely. And if we extend it a little bit more, then start using a package manager to transport them, deploy them, and test them. Let's start with SerDes cameras. So we all know about cameras and how kind of they work. They have the sensors which captures the image and then converts them into bits and bytes. For these, there are different technologies. But the SerDes cameras are unique in which they all carry a serializer or deserializer, which is basically converting the image into just a stream of serial bits. And for these, there are 2 technologies that we're going to go through, but they talk only between serializer and deserializers of the same type. And the benefit is that they just have a single cable between them. So that's the cool thing. You don't need to be having more than one cable to connect them. And if the camera is far, you only extend one cable and it's cheap and cost effective. Some of them carry image signal processors before the serialization of the image. For this one, they might be doing special functions like demosaicing the image, which I put a little bit of example in here, like could be converting the raw image between greens and reds and blues. And then when you receive it, you need to decode it. It could be doing the autofocus automatically for you, correcting or filtering the image, removing noise from it. So they could also be packed also in here. Specifically for this application, we're looking for cameras that are using cars, but they could be used in anywhere. Like we seen it in robots or.
So real quick, for those who know the 148X card, what industry? Automotive, consumer electronics? Automotive? Okay.
Tested measurement.
Just tested measurement? So in your pocket, your cell phone has a camera in it. That is not a SerDes camera. The technology behind it's the same. So MIPI CSI2 is the standard. That's kind of behind how the bits get packed. The serializer, deserializer, when automotive and robotics industries really started using this, went a little bit step farther because if any of you have ever done anything with CSI2 cameras, I forget how many millimeters the cable is. Like there's cables between the camera and your PCB, but it's like maximum of so many centimeters before the signal loss is too great and you lose an image. So the serializer, deserializer technology, Luis is going to go into those. That's what's there. But if you're not familiar with it, it's not just automotive. He's showing automotive. We have used the same camera, same NI stuff for the agricultural industry. So tractors, very similar. Robotics. So in factories, literally moving robots around with LiDAR automation. And then also consumer electronics, gaming headsets. You guys like, what is it? I don't even know what they're called. We have like 3 of them. The VR things, they make me nauseous, so I don't use them. But those things have cameras in them too. They're implementing eye tracking. And so Konrad, also Germany, developed a custom piece of hardware called the MIPI Pod. So even for our customers who are doing consumer electronics and aren't using serializer, deserializers, that allows them to take their MIPI CSI2 cameras and go to the NI hardware.
Yeah, here's an example of what they do. It's like we have the camera, the serializer, it gets deserialized and then gets decoded by the ECM. And it could be the other way. I mean, they could also generate images in case they were needed. So it happens both ways. Just explain a little bit how it's done. It's like we grab the first line and then the second line and so on. And we have some points in which the stream gets synchronized. Like, for example, in the first byte and then the last one. So that way you can tell where you are. But this is done by the chip. So we don't worry too much about this one. We care about it because we're going to see low-level packets later. But really, it's more the communication between them. And other things that are also packed in these small chips are I2C bus, which you can have I2C devices either on the camera or in the other side. But basically, in the camera, you can have more devices and be connected to the serializer, and it will also send that through the stream. We also have GPIO signals that you can use to control stuff. Like we've seen in some cases, like there was a customer who wanted to hit the camera to prevent it from getting frozen. So it just enabled an internal resistor and started to hit the camera, for example. So there are a million applications that we can use here. Also, you can use it to synchronize the generation of the frames on the camera. That also is just could be a kind of like a trigger. So let's say on the right side we have the UUT and it's going to be sending a pulse for every frame it wants to be sent. So that would be for triggering the frames. Sometimes they use that to validate that they're getting the frames at the moment they need them and not just receiving the stream. Let's list a little bit of the applications. So normal application would be like this one. You have the camera connected to the UUT and that is just the end product. But the things that we can do with the Flex Video cards are like loopback, for example, which is could be used like if you want to validate something.
Self-test.
Self-test. In fact, for example, we're gonna see two chips. The FPD-Link one that is from TI. It has a mode in which you can generate a pattern. So that way you can actually see an image and just with the chip without camera, and you can validate that it's just a loopback test. And then acquiring from the camera, we have a tap mode too, which is the card would act like it's not there with the UUT and the camera, and whatever the camera sends to the UUT, the FlexReal card would grab it and then send it to the UUT. But in the meantime, you can analyze what is getting received and even simulate specific images or I2C comments, for example. And generation, which would be, we don't have a camera and the card is just generating everything, the frames, the timestamp to the UUT. Yeah? Yeah, I went through this one. Another thing that we sometimes do in tap mode is to inject faults. And this could be, there is some data that is also sent, I call it embedded data, which is not only images. It could be timestamp. And we had a customer in which they were counting the frames. So you can actually send a frame counter and be able to tell every time you receive a frame, not in the image, but in the metadata, know which frame is it. In some cases, the other thing that could be done is be replacing the CRC of every packet and make sure that data integrity is good. And the generation, okay. There's hardware the loop projects that could be done with this one. It could be like, for example, you can either record, like let's think you have your PXI and you mount it in the car, you put the cameras and you start recording all the data. And then you can just replay that in a lab or your test bench. So that is one application. The other one would be software in the loop, which instead of getting images from the camera, you can just simulate it. We've seen that in some cases Unreal Engine is used. You've probably seen it, like the Call of Duty game was based on Unreal Engine. So this is just an example for it. And also I2C simulation.
So real quick, I don't know if anyone was actually counting how many different applications, not counting like in-vehicle. So in-vehicle would be camera to ECU. So you had loopback, which I don't know that I'd count that. We do use that for self-test. We'll leave it in there. Then he had record, you had tap, you had generation, you had hill, you had software in the loop, and with generation. So we had at least 7 different things. So I want to mention too, when we were starting the planning of this, Luis didn't know this, but I was working with him to kind of architect the framework for the API. We do hardware in the loop projects. We do software in the loop projects. That's not what we were doing with this particular test, but there were some things Luis would ask and I'm like, no, let's not do that. Or there were some things we were going to hard code a certain way. And it's like, no, because in my mind, I'm a lazy engineer. So I want to reuse as much of my code as possible. So I'm trying to have Luis actually make me the API that I can reuse on these other projects or keep extending it. So that goes back to the s'mores. Can I pause and think about something in a way that lets me say, I'm here today. This is my current goal. Is it an extra day, an extra week, an extra month to make my next project easier? And if the answer is an extra day, take the extra day.
So let's review what is going through the cables that we see before. So I'll leave you with SerDes we went through previously. MIPI is just the standard we're using. CSI2, the type of communication. And FPD-Link. FPD-Link stands for Flat Panel Display Link. This is done by Texas Instruments and is proprietary to them. And to highlight a little bit what's going through the cable is we get the power over the cable, that is going to be DC. And then we get the video, which is going to be between 770 megahertz. And then the control channel, which is going to be between 1 and 5 megahertz. And that's how they achieve to send so much data, because it's just one single cable. We run these up to 4K video and no lag. And one important thing when moving into the the FlexReal side is on NI, we use Python scripts to program the cameras. And this is going to be a differentiation with the GMSL ones, which they use C++ scripts. And this changes a lot the rules of the game because you need to do your API in order to accept both of the scripts. Yes?
I'll make a comment. Full disclosure, I'm the designer of these products. Daniel Hearn. Oh, there we go. Great. Just want to point out that last year, FlexReal 24 Q3 driver included some improvements for I2C, one of which is a vendor-agnostic configuration script format. So there is now in the FlexReal API, there is an additional, we still have this, but now there's an additional API which allows you to basically just have a comma-separated value list of registers that you want to write. And in fact, the API itself is done quite generically. It just defines a cluster type, and then you can actually define your own storage file storage format for the data that as long as you can represent it in the cluster that the API expects. So just FYI, that was released a few months ago.
And I think Luis will comment more on this, but like we really preferred the Python of the way because we were able to put a lot more debugging steps when we were running into scripts like the camera wasn't accepting the data, and we can put more debugging steps in the C++. I don't know, does the new thing cover that too? Does it allow us to get debug information back?
That release does not include that. We are likely going to lift that restriction moving forward.
Oh, that's very cool.
Fundamentally, that was put in place when the products was first released because that Python format is actually defined by the way TI's evaluation kit programming software defines it. And so we wanted to, we don't want to ruffle any feathers.
Yeah, I know. It was a lot easier for us to work with the TI than the GMSL, partly because of the extra stuff. Luis is good at Python, so he did a lot of extra debugging.
Yeah, it helps a lot because when you run the script, you can actually get a lot of information like when did you run it, the time it took, special registers that you wanted to monitor, and everything gets output in the script output. In fact, it was easier because a customer was requiring us to have the status of the serializer, deserializer, and the imager, and that was only one script. We either could split it into 3 scripts or just one, but we added some tokens throughout the script and later parsed them out, and we were able to get the status of that. So yeah, that's a very useful way. The Python helps a lot. I mean, you can get like...
Technically, there is an API just to also programmatically interact directly with the I2C interface and LabVIEW or the C API for FlexReal.
Yeah, I think we use that. I don't even know if I have this on here. We do use that API to do I2C COM post initial programming of the camera.
Here are more specs, but I think one of the most outstanding one is the cable length. I mean, we have tested these up to 13, 12. We use cables that length and still good, no problem. This has been very important because it's very common that customers or you might want to discard the hardware layer, and this has not been an issue so far. This one, I will explain a little bit on this one. Can you just, yeah. So the packets are going through the cable are going to be 2 types, either short or long packets. For these ones, short packets are usually start of frame and end of frame, and long packets are going to be your image or metadata. And the importance of the short packets is basically that you want to know where you start and when you end. And then long packets could be different ones. How does it get converted into packets?
Skip over some of this one. Yeah.
Yeah, this one is just an example how we just split the image in different lines. We just get serialized. This one is important because you want to understand how you're getting the image, which is basically if you're getting RGB, YUV, and that is how the the data is going to be streamed through it. Later, when you decode it, you want to know. This is just pretty standard for imaging. Just the packing. This is an example. This is like RGB 32, which you just get 8 bits per every pixel. So you just get the RGB values of every pixel. And as you can see, we just send one after the other one until we complete the whole image, which is going to be, I don't know, 1980.
So this is important because the data you get back, depending on what the customer wants you to do with it. If you're just logging it to disk, that's fine. One of the requirements we had for this API, and we've had for a number of customers, is to convert it to a human viewable image. So embedded in the packet type is it RGB 888? Is it RAW 12? Is it RAW 16? And that tells us all we get back are a bunch of bytes. We don't actually get an image. So for those of you who have never used these cards, it just looks like junk. So we have to understand how those bits were all packed together to make the pixels to build the image. And the NI getting started example kind of supports them all in a giant case structure, but we had to change things around a little bit because we actually do fault detection on the FPGA for the different types. And it doesn't fit on the FPGA. So we have different versions. So we have a RAW 16 version, a RAW 12 version, and we've written our API so that based on the camera type, our customer specifies, I have a RAW 16 camera, here's my starting script. They wanted something super generic. It picks the appropriate bit file behind the scenes that we've now have to maintain a bunch of. So put in bigger FPGAs.
Yeah, go through that. So this is a list of all the formats that are available. I mean, there are more. I mean, they follow the MIPI spec, but the ones that we use the most. I mean, RAW 12 is very common, and YUB, but yeah, usually we can get more of them. And the metadata, which we're gonna see them. Okay, this is not escaping. Here we can see, for example, our image, the start frame and stop frame. And this is important also because the example from NI doesn't come with frame rate calculation from the FPGA. It does it from the host code. But if the host code is running on Windows, you don't know if that is going to be delayed or not synchronized. Like, I mean, you want to get the real FPGA rate. So we customize this to measure when we get the start frames, and then we get that frame rate directly from the FPGA. Also because when we start adding more cameras, then you don't know how your system is going to be behaving if it's not the FPGA who's sending you the image, the time to calculate this.
That's a very good point Luis just brought up, is number of channels. So like he said on the host, if you're just looking at 2 channels and calculating the frame rate, it's probably accurate. We have 24 cameras at a time that we are logging to disk and testing. They may or may not be enabled test sockets. So we have 3 of the 148X cards. The customer can put in GMSL or FPD link. We have to auto detect whatever they've put in, and then they get to pick the camera type. It is a universal camera tester. So we had to kind of plan and test for a lot of this flexibility that was happening. And so that's why we chose to put some of the faults and things on the FPGA, because we were getting different behaviors if we were running 8 cameras, 16 cameras, or 24.
So how are these cards? Just to get a general overview, is we got an FPGA, which is our traditional FPGA card. And there's a mezzanine card, which is just a daughter card that gets connected to the FlexRio card, and it has its own personality. And by this there's a clip that we add into the FPGA, but it's used to be able to communicate with the daughter card, which ends up being the one that is carrying the serializer or deserializer, depending on how you need it. The models that are available are these ones. It's FPD Link 3 and 4 for 1486 and 1488, and GMSL 2 and GMSL 3 for 1487 and 1489. And for all of them, you can find 3 flavors, which are going to be 8 inputs, 8 outputs, and 4 in, 4 out. And depending on the configuration is what you can achieve. For example, tap mode would be 4 in, 4 out, and generation is only output, and so on. For input, it's acquisition.
Since Daniel's here, I'm going to complain about something he probably already knows. So go back. The 4-in, 4-out has a dedicated serializer and deserializer per channel. The deserializer card that is 8 channels has 4 dual channel deserializers. So we had to do a lot of special stuff because when we're programming, those 2 cameras have to be the same, which for us, it's kind of okay. We made the restriction to the customer that one bank of 8 cameras has to be the same type. So they can only program those all in the same script. That was a restriction we put in. We could have done channel pairs, but then we had to discover and implement aliasing, or I forget what GMSL calls it, but it's the same thing. Basically, we have to get through programming the serializer and imager and give them a different I2C address, because otherwise is channel 1 failing or channel 2 failing? And so it's just extra stuff we then have to maintain per channel that had there been an independent, and I know that was probably a cost solution, or space, could have been either. Space, yeah. But that was something that was a little bit harder and we wish would have been just, examples and had more stuff for.
Right. We'll talk about that later.
Okay. And to explain a little bit about the aliasing is because customer wanted to test the cameras at its default state, which is not changing the I2C device address. So since you have 2 cameras in the same chip, the chip needs to know which camera is it talking to. So then we do the aliasing, so the deserializer knows which address you are talking to, and the cameras don't know that it's actually, they are 2 in the same place and they have the same address. And talking about the software, this is pretty much how it looks. You have your clip that goes into the FPGA code, and then your host code. And here is to explain a little bit. In the bottom part, we have the mezzanine or the clip, which is the personality of this chip. And it changes because when you choose, for example, TI, you cannot swap and use GMSL cameras, for example, because TI only does FPD link. And this is embedded with the clip. So this limits also a little bit the flexibility. So you need to decide. You cannot change the camera.
Yeah, the purple part we don't touch. That's like the card we pick, yeah.
Yeah, so that way remain the same because it's always going to be the clip and we don't control this. And then on the FPGA is where we change what we're going to be decoding, and then the host code. To explain a little bit about the clip, it's just like a DLL that you put in your FPGA. It's very, very similar. It's just an easy way to describe the clip. And you can just, we've seen that you can just Google for clips that if Xilinx develop and it's available and open, you can use it and mount it there. So it's not limited, since FPGA could just be programmed as you want. So how did we start? So we started with the getting started example, and this is how we do it. You just go through the example finder, and then you need to browse a little bit, hardware input output, Flex Rio, getting started. And when you find only one example for all the cards that we mentioned, it's because when you run that example, it's actually your project template generator. You just need to choose which camera you want to generate the code for, and then it does it for you. You just point to the directory and give it a name, and it's going to generate it for you. And when you get back, it's going to be the project, which is a lot of code, really. Here you can see an example that we have acquisition, we have a common library and generation library, and depending on which model you are using is what you end up. But to summarize, you have the host code and the FPGA code. And here you can start customizing it for the application that you need. And from here, we wrap it around our API to reusing a lot of these BIs, because there's a lot of configuration and handling the FPGA internal state machine here that already is done by the example. So we just reuse it. Some of them were customized. Like, for example, if we start talking about what you get, if we open the block diagram, you can see here, it's a lot. And if you want to change something, you need to think twice what you're changing, because there are a lot of cables there and it's not easy to get a lot of. Once it's running, I mean, it's either you get the values asynchronously or you decide to move into a more modular design. But we understand this because this is just an example. So we needed something for our application, and this was our starting point.
And what Luis has at the top is literally what some of our requirements were. The independent channel control. That was huge. That's not part of the getting started example. The data logging per channel. Are we going to log or not, depending on what's happening? The frame rate calculation that we actually ended up moving down to the FPGA. The faults. So he mentioned, like he showed in the getting started example, the FPGA, right? But that's not what we're actually using. So if you listened early on when Luis was talking about APIs and making sure the interface is important, how many of you have done FPGA? Like, could we have done the same, call from our host to the bit file? We had to make what the same? The interface. So we have to support GMSL and FPD link cameras for this customer. They support more than that. So we tried to make the simplest interface to our FPGA bit file possible. And then based on the camera, we actually send down the fault conditions, and then the FPGA reports back information.
So you were using the same FPGA bit to support the...
We have 4 FPGA bit files, and based on what the customer picks for a camera, it deploys to the card.
So then you can have a different API for each FPGA clip, right?
We don't have different APIs. We have the same top-level API.
Okay.
So same top-level one that calls, and basically based on configurations, we'll load a different bit file. But because the interface on the bit file is the same, we were able to do that.
Another thing that was key on this is we talk about fault injection, but we didn't talk about fault detection. And here it was a requirement, and it needed to be done at FPGA level because the customer wanted to capture all the faults that happen. So since we were at first we were doing it at the host side by analyzing the images and the packets, but I mean
24 channels was too much.
and a 4K image, it's a lot. So we end up moving that into the FPGA and customize to detect this. And we end up creating the PI, and we also list here the reasons why we move out of the getting started example is because, well, it's not as Morse friendly as we saw before. It was really good to start, but we needed to log the data. And also another thing was to be able to pause the logging, because imagine logging 24 cameras 4K, then your hard disk gets filled really fast. So we end up deciding with the customer when to pause or end up baselining information of the core images. Another thing, there's a limitation on the PGAs because you can only run up to 4 channel displays, which is seeing the images that are acquired in real time. We tried to compile for more channels, and we were limited because of the PGA size, but we needed to see all of the cameras. So it was 8 channel display what we needed.
Got a question. Like, is it a requirement from your customer to actually display at the frame rate that the camera was capturing? What did you just do?
No, so...
Or did I just display every second or something?
Yeah, so this is one of the top tier 1 automotive customers, and they produce a ton of cameras, and this is for their validation lab. So they put the cameras in thermal chambers. So these tests, the biggest thing we had to do was make sure it runs for months at a time without them shutting down or rebooting the system. So the least amount of stuff we can do on the host possible, the better. It is configurable, so they could theoretically go in and say, I need to save a frame. The smallest limit is once a second. So 1 frame once a second on 24 channels. They typically don't want all of that data though, because it's too much for them. Because when they have 3 months of data for a validation test run, that's just garbage to them. So most of the time it's set for like 2 minutes. They have all these other crazy, they actually have like 5 different sequences that we run. And one of them, for instance, they power cycle the camera every like 2 minutes. But again, that's configurable. This entire system is super configurable and flexible because it's a generic camera tester. So we can test certain use cases, but we're still always ongoing support because, oh, we're running this way now and now it's behaving weird. Well, we didn't test that use case because we can't test every use case, right? So there's some use cases where we're like, oh, we didn't expect you to use it that way. We didn't test it, and they're okay. So we find bugs, but luckily with doing it this way, the way Luis developed everything, we've been able to go in and extend it or change things.
Another answer is that we don't need them real time, but we cannot, like for example, we need the 8 channels, even though we don't get them real time. We just get them, it was like every half a second or something. But if we don't get all of them, we would need to be stopping the PGA to get from the other channels. So that's the reason why we needed to be all of them on board, because if not, we would need to stop the PGA. And also, these cameras have one thing, which is when they get power off, they lose the programming. So every time you power cycle, you need to program them. Or also when you disconnect, that happens too. So for these, we needed to have all the channels working without needing to stop the PGA. Just running out a little bit of time.
You're good. This is good fun.
This is just a general overview on how the system was. And our final API looked like this way, in which we just have one single PPL, which was receiving the input like configure, start, stop, get the image data. And then the outputs were TDMS files, log files of events. Also, you can get I2C logs. And here we would just saving at that interval of time images into disk.
It's easy.
Yeah. It looks easy this way. But when we see the inside, it's like, okay, we have the 1480X, we call it, like could be 1486 or 1488, has its own model. And then we have the camera model, which is going to be receiving the information like, I don't know, current, voltage, the status of the images themselves.
And he said module, but what he means is single DQMH module, clonable DQMH module. Okay, so what that means is we have 24 channels. This clonable handles 8 channels. Then we add 2 more clones, right? And same thing, then he calls the CAM and the I2C, those again are clonable. So that was kind of one of the reasons we went with DQMH, is the ease of use to add clonable, because we didn't know, is the customer configuring 10 channels, 24 channels, whatever. So I wanted to mention, I know he said module, but I want to be clear, those are DQMH.
Yeah, these are DQMH models. And yeah, customers started requiring new stuff, and it was easier just to add new models. And we just started with clonable models because we knew there are going to be multiple cameras.
So that's a very specific example. The I2C, halfway through, they had us hard code a couple I2C channels that, every one of our cameras has this. They released the next build for their validation, and they totally removed a PCB and an I2C address. Oh no, we decided we don't have that anymore. Now that was hard coded in by us as a DQMH module, so now we had to remove it because it's no longer part of the generic. So Luis added, again, it was easy because he just added new feature, new DQMH module.
Yeah, we ended up with 4 different I2C models, and at some point we decided, hey, we can just build one generic one, and we just remove them. But it was easy because there were only calls to DQMH models, and instead of 4, we just replaced them with 1, the generic one. So that one, the LLP is also for the TDMS output from the image. This one used to be a parallel loop inside the getting start example, and we just send the bit file reference to a DQMH model, and we just launched them by separate, and we started saving internally with a helper loop in the DQMH model. We were running saving to disk here. And for the easy of use of DQMH, we just added our internal debugger, which is the logger, and we just save events specific to the state of our application. And well, it looks easy when you see it just like this, simplified. And this was also a DQMH model. So we needed to call this one from testend, and DQMH is very easy to be called from testend, very friendly to it. So you can see testend is actually calling these green rectangles, but those are going to be the SerDes PPL. So the good thing is that we changed the code, but the call from testend remained the same as we didn't change this one. So it was also good for continue supporting the customer changes on the performance and behavior of what they needed, but the calls from testend and the PPL itself didn't change. So this is a very big general overview, like summary of the application. So we have the camera with serializer and the imager, and then the SerDes PPL is going to be our host code and FPGA code, which started as a get and start example, and then we transform to the PPL. And that one communicates with the UI because, of course, customer wanted to have a UI for debug and configuration and everything that they wanted to change. And testing, which is actually the sequence that was going to be controlling and testing the cameras. Yes,
I was just going to say, this is the part that Luis worked on, and his whole API is really that SerDes PPL. And for good or bad, he also had the restriction of working within what I'm calling the customer's framework, which is the outside, the test stand. We literally, for all of them, have these sequences that have been built. And every single time we get a new UUT or we're working with them, for this common camera tester, we actually created and modified what we call tester specific in test stand. That is it. So we have certain things that we periodically log. They have a custom report model. They have a custom batch process model where we run all their UUTs. None of that code. We started 10 years ago with this. We're still using those same sequences, the same base. We were just able to extend and replace the functionality. So we are still logging CAN. We're still logging analog input, additional things as part of the tester, because there's a thermocouple in the chamber and they need to measure all of that. And that same code, again, keeps getting used, which is great, but now we've added new features with the NI hardware. Had we had DAC-MX, that would have been much easier to start with, but we managed to get there still. So any questions, I think? We don't have too much time left. Questions, comments, feedback for NI since they're here? Sorry, Daniel.
No, it's fine. I'm going to ask questions. I have some cards, and I'm happy to follow up with anybody who's got questions on any of this products.
And if you don't know DQMH, if I asked at the beginning, most people were or they didn't know at all. That is a whole session in and of itself. I personally love Tom's LabVIEW Adventures. That's where I send my interns to go watch. It's a YouTube channel to learn DQMH. It's fantastic. So if you haven't looked at it, it's a great way. And again, the clonable singleton architecture of DQMH, being able to do that for a per channel basis, if you're ever building an API, it's a great way to go.
And Darren did a presentation.
Darren did just an introduction to DQMH right before this presentation, so where the recordings come out, you can go see that. But you can also come talk to me. I'm the lead architect for DQMH.
Yeah, Becky, can you maybe just touch quickly on customer impact, how they were doing things prior with the one-up tester versus now, like overall, speed of integrating new cameras, that kind of thing? Yep.
So the customer typically uses the product development team gets proto boards with from TI chipsets and whatnot. And they even have some stuff with an FPGA. So there are some challenges there. So the customer, an example recently was, they're like, why do you only have 3 faults? I can do a lot more. I have the same FPGA. I'm doing this, this, and this. And he's like, what FPGA is on the NI card? So I sent the customer the specification. And he's like, I know, this is the exact same one I'm using on my SDK kit that I have with my camera. And it turns out, I'm like, well, how many cameras are you actually connected to on there? 1. So he has a lot more space on his FPGA to do stuff because he has 1 camera, we have 8. So that's kind of my request to NI is look at FPGA size and functionality and speed because customers get these SDK kits and it is using the same FPGA as the NI card, but it means they can do more. Another thing we put together that might be interesting for some of you in the audience is you are limited by size and what you can do on the FPGA and on the host code. Because has anyone in here done image processing? I mean, some of you guys have, right? Have you ever tried to view everything or process every image or look at every image? Even with 1 camera, it's often difficult, even on a decent computer. There are solutions for that. We've got demonstrations we've done with Radx. It's actually another NI Alliance partner. He makes PXI GPUs. They are fantastic. There are even LabVIEW libraries. He's worked with another partner that you can program your GPU with LabVIEW. And so it's a fantastic solution, but it is very expensive. So this customer is very cost sensitive. Previously, I'm gonna explain what their solution was. They literally would have, let's say the 24 cameras with an RF switch. The RF switch would go to a single box that had a deserializer in it. It would deserialize the data and build an HDMI stream. Then they had a camera capture card in a PCI computer. So they were switching between 24 cameras to this single mystery box. And the reason we had to do that repeated pixel faults, why we had to look for that, is the solution they used before, we get a lot of blank images.
But it wasn't the cameras.
But it wasn't the cameras, it was, and must have been, yeah. So one of the challenges for us is I'm like, we don't get blank images. We either have data or we don't have data. And we had a camera recently faulting, and it was faulting a little bit weird. But I think it's within the camera itself, but we're getting like 1.8 frames. So we're not getting a second start of frame, because that's what we're looking for when we're doing our, our frame rate calculation on the FPGA is the delta between start of frames. And so we somehow missed that because we ended up with a little bit of an extra big frame, but it wasn't 2 full frames. It was a partial one. So that's something that they're realizing, and they were very upset, and they were talking about the tester, and then they brought their product team in, and he's like, well, it's one camera. How often is it happening? It happened 3 times over 4 days. And he's like, oh, that's probably fine. That's within spec. So it is a challenge sometimes when you're working with the validation team versus the product team, because they have different expectations. Is that good, Joe? Did I catch you all that? Don't put an RF switch on cameras. It's just no. See, most of you are like, yeah, that's not a good idea. Although the NI thing is a lot more expensive. I will agree with that. But they're calling it their premium tester. It does do a better job of testing everything, and it gives them a lot more details they weren't able to see before. Because think about it. They had this black box deserializer that spit out an HDMI stream that then they had another card reading. So R&D is very happy because now they have the full LLP. So the customer's like, oh, wait, so if this camera is behaving weird, we can actually look. We capture, if a fault happens, we save the LLP. And then they can look at exactly in the stream what happened.
Is there any debug data in the stream to help out with that or no?
Depends on the camera. So there is metadata, but if it's not in the embedded or metadata of the camera.
It changes from camera to camera.
Yeah, it all depends on it. Like we've had some customers, yes, where we've had to do that. And they're like, monitor this GPIO line, and that'll tell us things. Other customers. And surprisingly, it actually shocks me a little bit. I don't know if Luis has experienced this as much, but like working with some of these customers who are making these cameras, even though they're an automotive company and they're making cameras that go in my car, they don't really do a lot of it. They package it. Like, so when I ask questions of the camera and how it's behaving, they're like, oh, let me go talk to Sony who made the imager. Like they didn't even know the register settings. They did not take the register settings themselves. They got it from Sony. So they subcontracted that part out. And a lot of what they did is actually just packaging it to be in vehicle.
Yeah, the information is very limited. Like, for example, for one of the cameras, we thought about asking, it was Sony, I think so, about how to generate like a color pattern, a black frame, a white frame. And they agreed and they sent us the configuration and we started using that to validate, because this test was supposed to run for days and days and it was very hard to
we
debug.
needed to fake a fault to make sure we could see a fault.
To make sure that we were detecting the fault. So we decided to inject, and when we configured these registers, then we generated the black frame and then we were able to test our FPGA.
So it's supposed to be like a CRC check at the end of each frame so you can check that?
Some of it is
Yes.
in the image itself. Like some of it's in the serializer, deserializer. So there's like a couple CRCs. Some of them you can fault and check, and some of them are you don't have control over. Because we actually did a hardware in the loop system for a robotics company, and they asked us to fault the CRC. And as we were getting into it, we realized we could fault like the image CRC, but not the full packet CRC or something like. I don't remember exactly which one. There's 2 different CRCs. One we can fault, one we cannot, because when we were serializing it back out, it fixed it.
When you look up for these cameras or the cards, you can look for pixel mode and tunneling mode.
Yeah.
And the first one carries the CRC all the way, like for example in tap mode. So even though we changed it in the FPGA, it was taken from what was received at the beginning and we were not able to.
And Dan, did you have a thing on that?
Oh, yeah, I was going to basically comment on that. The pixel and tunneling is a GMSL contact.
Yeah, well, this one was GMSL. Go
Yeah,
ahead.
the concept of a pixel and tunneling mode is a GMSL only concept, but in GMSL parts and pixel mode and in all FPD link parts, it is a lossy transmission. So meaning that like the data is fundamentally converted as it goes across. So the serializer on the camera, yes, it's getting a MIPI CSI2 packet. It's actually just taking the pixel data, formatting it according to whatever proprietary interface it is, GMSL or FreeLink, sending it to the other side where then it can reconstruct a new CSI2 packet based on that. And so if there is an issue between the image sensor and the serializer, that gets masked. Or you have to make sure that you're checking I2C registers on both sides of the link to see if they're detecting a fault. The tunneling mode that GMSL has resolves that issue because it actually passes the low-level packet directly from the image sensor across the link. And then once we have it in our FPGA, we can receive the low-level packet as we get it. And you can choose whether you want, there's some like bit detection correcting fields. You can choose whether or not you want the actual raw packet or if you want it with the 1-bit failures corrected. And then from there on, you can actually do stuff. But it's important to just be aware that like the actual link is not sending all the information that the image sensor is producing in all cases.
Does that solve it? Yeah.
Thank you.
Well, yeah, I think we're a little bit over time.
Tell them about the QR code.
Oh,
Yeah,
I think Dasha's got it. Dasha,
Yeah.
we have a QR code, more information.
Yes.
We actually have, Dasha made a great, we actually have control of a website now. So on our website, more than just the Konrad, full website, there's information about this presentation. I think you were going to put this up there when we're done. As soon as the video stream gets published, Dasha will probably add it to there as part of the landing page. Or if there's any other questions, feel free to follow up. I mean, Luis and I have lots of experience now with DQMH and cameras. He does more of the low-level cameras. I'm the one trying to make sure that the DQMH stuff plays nice.
Yeah. Yeah, it's a lot of work. But thank you so much for attending.